of the way in which the Earth works. In a different life, I worked on oil rigs in the mid-1980s. Subsequently, I went travelling for 6 months. Then I became a teacher, and I taught geology and geography for 26 years in both the comprehensive and independent sectors. I still have geology in my heart. I collect and sell Cornish minerals. I also lead sort of whistle-stop bus tours for American high school kids in Ireland, England, Scotland, and my favourite, Iceland. But my real passion for travel is still being fed by leading adventure travel expeditions with young people, and I've led 20 or so of those, and I'll be talking more about those later on the cruise. So what am I going to tell you? Well, this morning I'm going to tell you about the origin of oil and gas, about how it accumulates, how you can get it concentrated in an economic quantity to extract, how we explore for oil and gas, how we identify where those concentrations are, how we drill an exploration well to prove whether or not the oil or gas is there. Some of my memories as a mudlogger, more of which later, so my time working on the rigs, and then a little at the end about production wells. So, let's get started. What we're looking at is petroleum. And petroleum can occur in a solid form. So the top left there is what we call oil shale. It can occur in a semi-solid form, which is the tar or tar sands. Then we've got liquid oil and we've got natural gas. And what petroleum is, it's a naturally occurring hydrocarbon. What does that mean? It means that you've got large molecules of hydrogen atoms linked to chains of carbon atoms. So if you've got a very long chain, then that's more likely to be solid, something like tar or bitumen. Medium length chain, liquids, paraffin and so on. And if you've got a much shorter chain, that will be your gases, for example, methane. Now, we refer to petroleum as a fossil fuel. So that means it's formed from the remains of what were once living things. With petroleum, the vast majority of petroleum owes its origin to microscopic marine plants. You'd fit 10,000 on a pinhead. They're that microscopic. We're talking about phytoplankton, which means single-celled marine plants which photosynthesize. Think a little bit like the algae on the side of your fish tank. Now, this phytoplankton is what led to the origin of most oil and gas, and certainly led to the origin of the oil and gas in the north part of the North Sea. However, it is possible to generate gas from a different kind of organic material. So in the south part of the North Sea, the gas there's no oil, it's just gas, owes its origin to land plants, so a different origin. So what happens in the ocean to this phytoplankton? Well, you get a constant rain, if you like, of dead phytoplankton sinking down onto the seabed. Now, if it's in an area where there's plenty of oxygen, all sorts of worms and stuff, detrivores, they'll eat it all up. But what we need in order to get it preserved is what we call anoxic conditions. Anoxic means no oxygen. So effectively it's stagnant or very still water. And we tend to get that in very deep water. So if you've got deep stagnant water, anoxic conditions, we get a build-up of a putrid black mud, which is known as sapropel. And this contains a significant percentage of organic material derived from these plants. You need an enormous amount of this sediment in order to generate economic quantities of petroleum. So in order to do that, you need what's called a subsiding basin, an area where the crust of the earth is sinking down. So you've got a deep basin, so you can get the accumulation of great thicknesses, often measured in kilometers of sediment. Now, it just so happens that the North Sea is what's known as a graben, a fault-bounded valley. So because of tension in the crust, that tension is taken up by fractures in the rock, faults, and that means that the land drops down and forms a basin, a subsiding valley. Now, this was happening about 150 million years ago. And it's the starting point for the opening of a new ocean. But the North Sea is a failed ocean. It hasn't got any oceanic basaltic crust underneath it. What happened was that later the tension became concentrated excuse me, further to the west, and then about 50 million years ago, we had the opening of the Atlantic Ocean. But a subsiding basin and the accumulation of great thicknesses of what we become source rock. So the sapropel, the organic rich mud, would form a source rock, a rock from which the petroleum is derived. Typically, these are very fine-grained rocks, so muds and shales and so on. And in the northern part of the North Sea, the source rock is a black shale known as the Jurassic Kimmeridge clay, after the Kimmeridge region where it was first described down on the Jurassic coast. Now, I did mention that coal can also be a source rock, but that is much older, so the source rock's 300 million years old, and we don't get oil associated with that. We only get the gas that is found in the South North Sea. And that would have been, the coal would have been deposited in this kind of environment where, again, you've got stagnant anoxic water, but it's stagnant pools rather than really deep water. So we've got our source rock, rich in organic material. How are we going to change this sapropel, the source rock, the mud, the black shale? How are we going to generate the petroleum? Well, what we've got to do, basically, is cook it. So we have to go into what's called the oil and gas window. So by deep burial, and temperature does increase with depth, if we bury these rocks to a depth of between 2 and 5 kilometres, the temperature will get up to the right temperature to cook the source rock. So we're talking between 65 and 150 degrees centigrade. So what's happening is that those really big hydrocarbon molecules are being broken down by the increase in temperature. They're being broken, so the process is known as cracking. And actually, when we refine petroleum, we do the same thing. We heat it up to release the different fractions of petroleum, whether we go from crude oil all the way up to aviation fuel. So this cracking then breaks down these large hydrocarbon molecules. During this process, you get a little bit of gas being generated, and that exerts a pressure on the grains, and it opens up micro fractures between the grains. This allows that early formed petroleum, whether liquid or gas, to get out of the source rock. This is known as primary migration. Once it's got out of that fine-grained black rock, it will then get into a secondary migration phase. So it's moving through a rock which is both porous, it's got lots of holes in it, and permeable, and that's the really critical thing. Permeable means that those holes are all joined together. So it may be that it's permeable by virtue of interconnected pore spaces, as shown in this slide, the gaps between the sandstone grains, or it may be in some other rocks, for example limestones, that it's the interconnected cracks in the rock, tiny joints and so on. So we've got this migration, this moving through the rock. Why does it move? Well, the petroleum, the oil and gas, is less dense than the other pore fluid, which is typically water, and that's why it will tend to rise. And it will keep on rising right up to the surface to give you an oil seep or a gas release at the surface. And there are a few places in the world where this occurs naturally, but that's no good for economic extraction. What you need is a trap. You need something that's going to stop this migration from getting all the way to the surface. So I mentioned that these rocks are permeable, the rocks that it's moving through. So what you need is a rock which isn't permeable, an impermeable rock that sits on top of those permeable rocks. So it's on top, so we call it a cap rock. And this is what we call a trap. So it's stopping any further migration and leading to the critical thing, the accumulation, the concentration of the petroleum. So typically within this accumulation, this reservoir as we call it, and it is a reservoir where the oil and gas is trapped between the pore spaces. It is not a lake underground. It's like a sponge. If you think of it in that way, that's fairly close to it. So usually you'll have a layering there with water, which is more dense at the bottom, and then you'll have your oil, and then you'll have a gas cap at the top. Now, one of the commonest types of traps is an arch type fold, A for arch, A for anticline. And these were amongst the first traps that were recognised, and indeed when they were searching for these in the States, some of them were so obvious, as shown in the slide here on the right-hand side, that it's what's called a sheep herder's anticline. But when they first started drilling, it was just hit and miss. Okay? So 1859, at Titusville in Pennsylvania in the United States, the first oil well to get any oil. They only got 25 barrels a day, but they'd kind of lit the blue touch paper. This was quite exciting. The first really big discovery was in 1901 at a place called Spindletop in Texas. Now, this is the Lucas Gusher. If you do this on an oil rig, you've made a very, very big mistake. Okay? These things pretty much don't happen anymore. But in the early days, it was very common, and they drill into an overpressured formation where there's a lot of gas pressure, and it would come out naturally and be going hundreds of feet into the air. So initially, this gusher was losing 100,000 barrels of oil a day. And it took a little while before they were able to what's called cap the well and get it under control and start to get the extraction of the oil. And it soon became apparent that there was big money in this. So everybody was doing it. This is the same reservoir, Spindletop. All of those wells are drilling into the same reservoir. So after a while, it became recognized that there were certain geological conditions in which you got the accumulations of petroleum. In the north part of the North Sea, we have quite a variety of different oil traps. So some of them are to do with folding, when the rocks have bent at depth, where solid rocks can flow, albeit on a geological timescale of millimeters in a million years or so, where rocks have been faulted or broken, and that's put impermeable rocks next to permeable rocks. We also have situations where you've had a cap rock, an impermeable rock, draped over previously deposited reservoir rocks. They've all got that same combination, though, of source rock, reservoir rock, and cap rock. So I mentioned earlier the North Sea Basin. Great prospect, big subsiding basin, and very thick source rocks. Now, in the North Sea area, the first petroleum to be found was they found natural gas at Groningen in Holland. I think it was in the middle of a beetroot field. That was 1959. Now, as soon as they'd found that, they thought, oh, that's interesting. I wonder if there's any other hydrocarbons in that area. So they started to do some surveying offshore. So here we can see a survey ship, and it's towing a lot of what are called hydrophones. They detect shock waves, and the string of hydrophones can be up to 3 kilometers long. So in order to make the shock wave that's going down to the seabed, they used to use explosives. These days they tend to use compressed air guns. So they'll have a sequence of explosive releases of compressed air. So the shock waves then transmit down through the water, through the sediments, through the rocks. Some of them will come back directly back to the hydrophones or detector. Some of them will be refracted, which means that they'll be bent because they're going from a medium of two different mediums that are of different density and therefore will transmit the seismic waves at different rates. So what we're identifying is seismic boundaries between layers of different properties. So here the sensor is shown on the seabed. More commonly, it's actually towed behind the ship. Now, one of the things I love about doing these cruise talks is I learn something new on every cruise. And I have got Peter to thank for telling me that something that I was told when I was working on the rigs was not true. So I was told, oh yeah, we always let off a small charge first to scare off any cetaceans, any whales or dolphins. But Peter tells me that actually that just makes them inquisitive, so they just come and have a look, which is going to be pretty unfortunate because some of those explosions are pretty large. So this is a more detailed diagram illustrating this setting off a shock wave and then it going down into the rocks and being reflected or refracted back to those detectors. So it works best where you've got rocks with very big density contrasts. And in the South North Sea in particular, we have what are called salt domes. And salt is of much lower density than the surrounding sandstones. So it makes a very strong seismic reflector. So we've got plenty of these salt domes in the south part of the North Sea. So September 1965, this little rig, BP's rig, the Sea Gem, found gas in the West Stowell field, 42 miles off the Lincolnshire coast in the south part of the North Sea. Hooray! Sadly, the celebrations were fairly short-lived because at Christmas they were moving the rig off the initial discovery well and it collapsed and sadly 13 people died. But the exploration did continue and over the coming few years, they found a lot more gas in the South North Sea. So they were looking at the Lehman Bank field, the Indefatigable, easy for you to say, and the Hewitt field. So these salt domes, the salt, because it's low density, will tend to rise up, a bit like the blobs in a lava lamp, will rise up, and that will displace the surrounding rocks and make them into an anticline, effectively. I don't like it though, because as a mudlogger, as somebody taking the samples, in order to drill in salt, you can't use a water-based mud, because water will dissolve the salt and then you get a borehole that you have no idea what the volume of it is. So you have to use a very special polymer-based mud, very expensive, very specific properties. But in order to wash the samples, you've got to wash those samples in diesel. And even with gauntlets up to my armpits, I'd come off a rig after drilling salt with really flaky skin, horrible stuff. And then they had to actually wash all of the cuttings before they were able to dump any of the waste rock over the side. So we got our first North Sea natural gas coming on shore at the Easington Gas Terminal in Yorkshire in 1967. But it wasn't very long, only a year or so, before the companies lost interest, because there was a situation where there was a ban on gas exports because the prices were pretty low. And that meant that the only buyer was British Gas. So now they weren't interested. However, the situation was completely transformed in 1969 when Phillips Petroleum found oil at Ekofisk. So this is in the central part of the North Sea. So not gas, but oil. And this was with the source rock, the Kimmeridge clay, which I mentioned earlier, and the reservoir rock here was, rather than a sandstone, it was in chalk, which is a variety of limestone with lots of tiny fractures in which the oil resides. So over the next couple of years, we got Ekofisk, we got the Forties field, which is enormous, the Brent field, the Piper field. So we had plenty of oil being discovered. 1973, the world oil price quadrupled, and then in 79 we had another oil crisis, and we had a tripling of the oil price. So everybody wanted to drill for it. In the early 1980s, UK was a net exporter of oil, and by the mid-90s, we were also exporting gas as well. So by about 2015, we were, one of the world's most active areas for drilling for oil, with maybe 160, 170 rigs in the North Sea. However, this situation has changed. In the following years, the North Sea oil and gas industry became quite stressed. They needed support from the government. The situation was, that we had probably over half of the reserves, half of what is there available to extract, had been exploited. It's extremely difficult to give an exact figure on this because occasionally you'll get new discoveries, not so common these days in the North Sea because it's been so well explored, but you do get some. But what's also important is new methods of extracting the oil. So we've got techniques now that can extract a far higher percentage of oil than we could in the past. And this makes it very difficult to forecast exactly where we're going with the amount of oil and gases there. So how do you actually drill for it? So I'm just going to give you a little video here. There's no sound on it. I'll do a little voiceover on it. So we've talked about the geophysics, the seismic surveys using the shock waves to locate where the structures where the petroleum's accumulated are. So we've located our oil traps, and now we want to find out, well, is there actually any oil or gas there? So what we need to do is we need to use an oil rig. Now, in the south part of the North Sea, it's quite shallow, so we use rigs like this. This is called a jack-up rig, and it can operate in water up to about 120 metres deep. So you tow it out to sea, and then these legs ratchet down until they're on the sea floor. You drill your exploration well, and then when you've finished, you jack the legs back up, and you tow it to a new location. In deeper water, though, we use these. These are called semi-subs, and these have large pontoons which are flooded with water, so the rig sits a bit lower in the water to give it stability, and it is then anchored to the seabed. So it will move up and down in heavy weather, but remarkably, these can keep drilling even if the rig floor is going up and down by 6 meters. And then after the storm, because of inertia, the sea is dead calm, and the rig is still going up and down. So this is kind of the anatomy of an oil rig. So we've got this big tower, which is called the derrick, and we need that because when we're putting pipe into the hole or taking it out, we don't want to do it always with the single units of drill pipe. A single piece of drill pipe is about 10 meters long. So what they do is they put them on in those 10-meter lengths, and then when they are pulling out of the hole, they'll pull them out in stands of 3 pieces of pipe. So that we're talking 30 meters, roughly 100 feet. And that's why you need the tall derrick to stack all of that pipe. And then you'll run it back into the hole in sections of 3 again as well. So the drill pipe is attached to a thing called the Kelly, which is hexagonal, and that sits in the turntable, which is on the drill floor, and it's that turntable which gives you the rotation. We circulate mud through the drill string. I'll show you a short video in a moment which makes this clearer. And mud, it's a very sophisticated thing. The mud engineer will get very angry if you say, oh, it's just mud. It's got very specific chemical and physical properties. And that mud circulates through the middle of the drill string and then comes up in the sort of the hole between the drill pipe and the walls of the borehole. And then we add on new sections of drill pipe as the hole gets deeper. So let's have a look and see how we do that. So this is an example of a semi-sub. We've got a big derrick here so that we can stack up our drill pipes. On the seabed, we've got a BOP stack, blowout preventer. Talk more about that in a moment. Those big blue things are the mud pumps for pumping the all-important mud. Here's a drill bit, a tricone drill bit. We'll look at another one of those in a moment. That then is lowered down in a large diameter casing, a big metal tube. And that will go down onto the sea floor where there's soft sediment. And the soft sediment then, you pump water at high pressure through the drill pipe, and that will jet the soft sediment out of the way. And that will just spray out out of the top of the casing, this metal pipe, and will just form a pile around that metal pipe. So you'll see it here being lowered in, and now they're going to jet it and squirt all of that mud out of the way. There it is. And then eventually you'll start drilling properly. You'll drill into solid rock. And when you're drilling into the solid rock, before you do that, you're going to put a pipe on top of that piece of casing that connects it right up to the rig, and that means that you've got a closed system, so you can pump. Here's the mud being pumped down the middle of the drill stem, and then it's going all around the bit there, and it's carrying those cuttings back up to the surface. So it'll lift the cuttings, it'll lubricate and cool down the drill bit, and it will also combat pressure. So if you do drill into anything which is under pressure, the density, the weight of all of that mud will hold it back. So that's the basics of how what we call spud the well, how we get started. So there's those big old mud pumps as well. And because we know the volume of, there we go, we know the volume of mud being pumped by those by the mud pumps, and we know the rate at which it's being pumped, we can calculate quite accurately the depth from which the cuttings are coming up to the surface. So here's a load of the drill bits. These are called tricone drill bits with their 3 cones, and the teeth on them generally are tungsten carbide, okay? And it's this tungsten carbide which is hard enough to grind its way through the rocks. So every now and again, you're going to need to trip out, which means you're going to need to take the whole drill string out. And in the North Sea, many of the wells that I worked on, we're talking 3 kilometres. So that's going to take a while. Why are you going to need to do that? Well, you're going to need to take out the drill bit to change the drill bit. They do wear out. And also, in order to stabilise the walls of the borehole, you need to run down more of this metal pipe, run in more casing. So let's have a look and see how that's happening. So we're taking our drill bit out, and then we're running in the steel pipe, the casing, and then we're putting down the drill string again. And what we do is we put in cement, a slurry of cement, and then the black ring there is a plug that's separating the cement from the drilling mud. And then that will push the cement up that hole between the drill pipe and the walls of the borehole. And that will cement it into place, and then you just carry on drilling and repeat. Oh, let's get that. So when the mud comes back up to the surface, it goes over these machines. These are called shale shakers. And they vibrate, so the liquid part of the mud goes down through them, and that is recycled. The cuttings, most of them will just get dumped over the side if it's water-based mud. My job as a formation evaluation geologist, or mudlogger, was to collect samples from here. And I would collect the samples because of doing what's called a lag time calculation, knowing the rate of pumping and the volume of the mud pumps, knowing how many pump strokes had gone. I could say, right, that's the depth that sample's come from. So I'd take the samples, I'd bag up a load, and they would be sent off to the laboratory, but then I would have to look at them in the laboratory. So we'd have a little unit, and we'd wash the sample, we'd look at it under a binocular microscope and assess what rock types were present. We'd also look at the sample under UV, because if there's any petroleum there, it will fluoresce quite brightly. And we would also, I kid you not, put it in a food blender and grind it up. And then we would test any gas that was coming off with a gas chromatograph. So we could get a great deal of information. And all of this information would be plotted on a mud log. Now, these days, it'd all be done on computer. When I was doing it, it was a rotring pen and a stencil, and it took forever. If they were drilling really fast, we always worked 12-hour shifts, so I never knew where I was going, when, or for how long. So sometimes it was I'd go out for 3 days. Sometimes, oh, you'll be back in time for Christmas. I'll be away for Christmas and New Year and be off for 5 weeks. And you would work 12 hours every day. Sometimes you would have to work longer than that if they were drilling very quickly, because you'd have to catch up on doing your mud log. But you'd have to work particularly hard if you were starting to see what's called a show. If you started to see a hint that maybe there were some economic hydrocarbons down there, then the well site geologist, who's the one that got paid the money because they were making the decisions, would say, right, we want to send down a core. So coring is where you use this donut-shaped bit studded with industrial diamonds, and it's a much slower process, drilling with these. And when you get the rock up, you'd be there on the deck, up in the Arctic Circle, horizontal sleet, and you'd have to be cutting up these 1 meter length. And this stuff is, it's 7 or 8 inches thick, cutting it up with a diamond saw, putting it inside a fiberglass sleeve, putting 2 big rubber caps on the plastic caps on the end, and then using terry clips, like the hose clips that you get, to make those really tight, dipping them in wax to seal it completely, and then putting it into a box, labeling all the box, nailing it shut, and then you imagine lifting those was hard work. So you'd be doing that for 12 hours in the middle of the North Sea, in the dark, in a hailstorm. It was not great fun. So, if you do get into a formation where there is pressure, as a mudlogger, we'd be the first people to see that. So we weren't just doing the recording what came out, we also had a safety role as well. So I mentioned this device before, the blowout preventer. So this is sometimes they call it a Christmas tree because it's got so many valves and pipes on it. And this usually will sit on the seabed, and it's there as you get out of jail free card. If you get an uncontrolled release of pressure, so like the gushers that we saw at Spindle Shop right at the beginning, then this could completely cut off the well. Very rare for that to have to be done, because people like me would go, oh, hang on a minute, that mud's coming back a bit faster than it should. So you call up the mud engineer and you say, yeah, I've spotted that too. So what would he do then? Well, the first thing that he'd do is increase the pump rate, and that would combat the pressure. But you don't want to keep doing that, because then you can overpressure the formation and break down the sides of your borehole. So while he's doing this slightly higher pump pressure, he'll also be weighing up the drilling mud. That means he's making the mud denser. Remember I said about very specific physical properties, by adding a dense mineral called barite. So they'll add that and it'll weigh it up, and down you go. So that then would give you a way to combat that pressure. So there's me with less fat and more hair, probably about 21, when I first started in this game. So that was in the mid-80s. That was on a little land rig in Scotland, in one of the oldest units that the company had got. Before I went off into the North Sea, though, I had to go to the Robert Gordon's Institute of Technology in Aberdeen, Scotland. And there, I had to do safety and survival training. And I was going to be working a lot of the time in the Norwegian sector, where they're very up on the old health and safety. So I had to do a 2-week course. So you've been out for an evening the night before with the boys, and then you have to get into your wet boiler suit and then sit you down in this machine, and they say, right, you've got to do up your seatbelt. Don't get out until the bubbles stop. So this is a helicopter simulator, 1.2 million quid of helicopter simulator. So what they do is they've got a swimming pool with a big wave tank, and they've got guys with high pressure water hoses spraying on you. It's dark. They put you down under the water, they spin you around, you wait until the bubbles stop, because otherwise, if you're in real life, you might get chopped in half by a rotor or something. And the divers are there to help you, and then you come out of this thing, gasping at the surface, and then you have to swim over to a capsized life raft and right the life raft and get into it and all sorts. And there was also lots of first aid courses, and I saw the gnarliest, the beefiest, rough-looking roughnecks and roustabouts, so the guys that worked on the drill floor, visibly pale and keel over with some of the slides that the first aid people showed us. I mean, you know, hands like hamburgers and all sorts of horrible things. But we also did firefighting. So I had to go into, I'm sure many of you will have seen, if you see a fire station, they've got this tower. Well, inside that tower, there's a maze of rooms, many of them with doors with no handles on. They'll have a gantry in there as well. So we all donned the breathing apparatus and the protective clothing and so on. And we had to crawl in through this tunnel and take out big, heavy buckets of sand, and then had to go along this gantry, climb down into an area, and it was all filled with smoke. They were burning pallets in there, so it's real smoke. They've got gas burners on, so it's super, super hot. You can feel the tops of your ears starting to burn, and then you find the dummy, and it weighs as much as you do, so you struggle back up the gantry, and then you find this door, there's no handle on it, and then your breathing apparatus alarm goes off, and eventually you get out with a whole new level of respect for the fire service. So that was all very interesting. And we also had to do lifeboat rescues out in the North Sea as well, in Aberdeen Bay. So most of my work was in the North Sea. So I did a lot in the Norwegian sector in particular, up in the Arctic Circle. So go away for 2 weeks and not see the light of day. And then I also did work in Syria, in Turkey, in Tanzania, and in Kenya as well. But going out to the rigs in the North Sea, you'd go. I can remember my kid sister when she was about 7. She was at school, and they were all saying, "Oh, yeah, what does your family do, and how do they get to work?" She goes, "My brother goes to work by helicopter." So, fantastic. So he used to go to work in these Sikorsky S-61 helicopters, great big beasts. Incredibly noisy, dressed in a full survival suit. I did, on a couple of occasions, get whisked off a rigs in the South North Sea in the tiny little Bell helicopters, and the pilot was a Vietnam vet, and it was like a fairground ride. A bit more excitement than perhaps we really wanted or needed. So the first rig that I went off to was called the West Venture, and I discovered when I arrived that its sister rig, the West Vanguard, only 2 months before, had actually had a blowout, a gas blowout. And this was about 100 kilometres off the coast of Norway. And the reason that I said these are very rare, but the reason that this one happened was that it was very, very shallow gas. So it wasn't where you'd necessarily expect to find it. As you can see, the sea is kind of boiling there. 79 crew were evacuated. I met some people who were on it, and they said, you know, getting into the water, you just went down and down and down, because it was like jumping into foam. And the last people to leave, actually, the management, they climbed down the legs of the rig and then swam away in their survival suits and were rescued by their support vessel, which was called the Black Ice. Now, this rig, the Maersk Endeavour, is a jack-up rig. Jack-up rigs, remember, in the shallower water. So this was a rig that I was on in the south part of the North Sea. The support vessels look like this. You can see at the stern there, right at the back, you can see a person for scale. Now, before I was on this cruise, for 2 weeks, I was on the Balmoral. And this was the view from our porthole window way before the storm started. Okay? After that, they very quickly battened down the hatches, and our porthole was locked shut for several days. It was quite interesting. And we were told, oh yeah, Storm Kieran, biggest storm for over 50 years, 60 years. Well, the last really big storm was in the first week of November. No, it was in 1987. And I was offshore at that time. And it was pretty lively, to say the least. So here we are in the middle of the North Sea. Oh, there we go. And that support vessel, I showed you how big it was before, completely disappeared in between the waves. And the noise of the screaming metal, the legs of the jack-up, was incredible. When you're working 12 hours a day for 2 weeks, 3 weeks, 4 weeks, 5 weeks, when it comes to crew change day, you really want to get off. And if there's any delay, you're really not happy. This is one of those Sikorsky S-61s, and unfortunately on this particular day, there was a delay. And I don't know where it came from, but some duck came from nowhere, had an unfortunate interaction with the Sikorsky, and it was shut down for a couple of hours while they checked the rotors. And then off we went. But I did have another incident in the South North Sea where a rookie, a new guy, had gone out into the south part of the North Sea without his passport. So they wouldn't let him offshore. So he had to go home and get it. And in the meantime, we got fogged in. And I had to spend an extra 3 days on the rig. So, yeah, he wasn't very popular. Sense of humour failure. So I've mentioned that on the rigs, it's all or nothing. You're either working absolutely flat out, maybe doing 14-hour shifts or whatever, really, really going for it, or if they're pulling the drill string out, once you've caught up with your mudlog, you're in what we call logging position number 1, which means you sat there with your feet up. So I did also do work in other destinations, so in the Syrian desert, it was very flat and stony, logging position number 1. There wasn't a great deal to do out there, so if I had any downtime, I'd walk as far away as I could from the rig until I could just see the derrick in the distance. We had some huge dust storms, which were pretty spectacular, and you would smell the herds of camels before you could see them, filthy creatures. Sometimes the highlight of the day would be when a dung beetle flew in, landed on its back, put its legs in the air, and eventually righted itself and then departed. In Tanzania, we arrived at the rig by a light plane, and the locals had to shoo all the ostriches off the runway first before we could land, and then once we landed, we had to wait for about 10 minutes for the dust to settle. And that was the little box that I spent 12 hours a day in the middle of Tanzania in the bush. I got very good at mending the air conditioning with brown paper and string. You have to be quite self-sufficient. Now, in the North Sea, when it's big and stormy, sometimes you'll have the letters WOW on the mudlog, which means waiting on weather. But when I worked in Kenya, I once literally had to write this on. I had to put WOL, waiting on lions. Nobody would go outside. And then a week later, WOP, waiting on president, because he was visiting the rig. So once we've done all of the exploration that I was involved in, we want to get the oil out of the ground for production. So this is a huge production rig. They're massive. This is Clare, up in the North Sea. So this one then started producing, I think, 2005. Now, don't think it's just a single borehole. What they'll do is they'll have several boreholes that will pan out. They can steer where the drill bit goes, and the end of the borehole might be 1 kilometre away from the rig. And this is to exploit as much as possible from the reservoir. The recovery factor, how much of the oil you can get out, varies. There's always going to be some petroleum left in the rock. It'll be stuck in the very, very small pore spaces or actually sticking to the grains. On average, in the North Sea, you'll maybe get 35% of the petroleum out. Gas, though, much higher, maybe 85%. So the primary recovery, the first stuff that we get out, is powered by the natural pressure of the gas. Later, you might inject gas to force the oil out, or you might inject water, or better still, steam, because steam will help to break down the sticky, larger hydrocarbon chains. So we've got several stages of recovery, whether it's from the natural pressure, whether it's pumping with water, or whether we're using hot water or a variety of chemicals or gases to get the most oil we possibly can out of those rocks. So, a few takeaways by way of summary. First of all, that petroleum is a naturally occurring hydrocarbons, and we've got solid, liquid and gas. They're organic in origin, and remember, from phytoplankton, microscopic plants. That these, when they accumulate in conditions without any oxygen, form a sap-propelled mud. That this, when it's buried deeply, undergoes maturation in the oil and gas window, and that will lead to the organic molecules, the hydrocarbons, being broken down into petroleum. We then get the migration out of the source rock into the reservoir rock, and then into the reservoir, where we've got a trap, an impermeable seal. We locate the traps using geophysics, like seismic surveys, and then we do exploration rigging to prove what the reserves are by mudlogging and also by coring. We also sometimes run a variety of tools down the borehole to look at other properties, like how porous it is, so how well it's going to flow. And then finally, the production rigs, different ballgame altogether, huge exercises, and that roughly half of it's gone. So, my next talk, a bit corny, but there you go. My next talk will be called When the Going Gets Tough, It Makes a Good Bar Story. And that's because if you went home from this cruise and people said, oh, how was the cruise? You go, oh, it's fine. End of conversation. But if you'd been with us on the Balmoral, you'd have had a long bar story because things weren't going quite according to plan. And that's what people tend to find interesting. So I will share with you the stories that I would tell you at the bar in that one, which should be tomorrow, but do check the Daily Times. Following on from that, I'm going to follow one of my passions. Those of you that attended my Barbados talk might remember I was rather passionate about caving. So I will talk about the wonderful world of caving, the great indoors, in my talk, Mud, Sweat and Beers. So exciting, amusing, and some really beautiful shots. And just finally, Callie mentioned this yesterday, We do guest speaker lunches. I'll be doing one today at 12:30. If you're interested in that and want to come along and chat about what I've talked about already, or about the adventure travel and so on that I'm going to talk about later, then just inquire at guest services. And do remember that Callie is also doing one of these, probably on the 12th, but you'll need to check that again with guest services. So, thank you very much. Enjoy the rest of your day. If you have any questions, I'll be at the back.